This is a pre-recording about script geometry, and the definition is very simple. You just take sets of points and planes and lines and so on, together with the boundary value map from one into the other, where the boundary of the boundary has to be 0, and well, there is a notion of tightness in scripts, which means that the number of closed cycles, closed functions, these are things with boundary. 0 is actually equal to 2, so that on a certain cycle you can only have exactly 2 orientations which are 0. And every cell is attached to a boundary which can have only such 2 states, 2 orientations, which have boundary 0. That is called a tight script. And the amazing thing is that lines in tight scripts, one-dimensional cells, can only have 2 points. So you don't have to assume that the line has 2 points. It is provable that it has 2 points. And also two-dimensional cells, if they are tight, then they have to be bounded by a polygon automatically. It cannot be something more complicated or so. So in a way, this notion of tightness gives you what you want. It gives you the geometry you require. The geometry is, as it were, originated from tightness. And in fact, what it means, tightness, is that any cell has local homology 0. So it's like kind of Poincare lemma. So it's a minimalistic discrete form of a Poincare lemma, which automatically defines lines as going from one point to another point, and two-dimensional cells as polygons. And you can write down many examples of such scripts. It's very similar to CW complexes, but the difference is that CW complexes have to be defined as locally Euclidean. You have to define them separately. Whereas scripts are purely combinatorial, you just have the notion of tightness and that's all. So that the point is that three-dimensional cells are no longer polyhedra. So the notion is a little bit more general than the CW complex. So, and you cannot really prove that. I mean, there are examples of three-dimensional scripts which are not CW complexes, but you can always refine a script to a simplicial complex. But the point is that this cannot be done in a unique way. There are many canonical ways, so to speak, in which you could do that. So it's not really replaceable by simplicial complexes either. So it is, in a way, there's a lot of things to be studied still, three-dimensional ones. Two-dimensionals, we more or less know what it is, because they are CW complexes basically. And you can give examples of that which are in our text, like the projective plane, Klein-Bottle, torus, and several models of the projective plane, which involve pentagons and so on. There are also there's also a model of a parallel world where you can step from one to the other and back in a twofold covering way. So these are examples which you can verify in the text, which should be read and studied, and then you can put questions later on. So for the time being, let this be all of my minimal lecture for the time being. So thank you and see you later.